Hello everybody, welcome to the latest edition of the Physics Corner, a series of videos in which we set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today we're taking a peek at something called the vector product, and we're going to discuss magnetic forces as an example. So, let's imagine the following situation. Suppose we have a proton moving through the air at some average speed of 27 meters per second. The magnetic field near the surface is 26 microteslas pointing due north. What is the force, specifically magnetic force, experienced by the proton if it is moving due north, or it's moving to the east, 30 degrees north of east, straight down, that means towards the ground, or straight up, meaning away from the ground? And how do we solve for all these different situations, and why is it different in the first place? Okay. So the knowns are the charge of a proton is a positive 1.6 times 10 to the minus 19th coulombs. Here is the speed, and here's the magnetic field strength put into scientific notation like that. I've also included the direction, which turns out to be vital for these discussions. Okay, so what is magnetic force? Okay, and how do you calculate that? This is a little bit different than, say, gravitational force or electric forces. Those are also vector equations and have vector results, but the directions were very easy to come by. I mean, gravity only goes down towards the surface of the earth, right? And an electric force either goes along the direction of the electric field or in the opposite direction of the electric field, depending on the sign of the charge. And those are pretty easy, and there's not a lot of real deep thought that you need to put in to find those directions. But magnetic forces are a little bit different because they involve something called a vector or cross product. So, in the previous video, we discussed a little bit something called a scalar or dot product. And that idea was you take two vectors, multiply them, or can calculate a product between them in such a way as to create a scalar result. So the classic example in physics is the concept called work. So you multiply a force times a displacement, which are both vectors, but out of that comes a scalar quantity, okay? But there's another way to multiply vectors, and that's to multiply two vectors and come up with a vector quantity as a result. That then is called a vector product, as you might imagine, or sometimes called a cross product. So the term cross comes from this little symbol here. So in the scalar product that we've discussed previously, it was a big fat dot, and that's got the nickname dot product for that reason. This is sometimes called a cross product because the symbol is a cross. Now notice this is not a letter X. And in fact, if you see this in official print, in say a textbook or online, properly drawn, it isn't a letter X. It is a little bit different. It looks like a letter X, but it's not. First off, it's elevated. Notice it's above right here, so it's not on the same level as the letters are. But it's also a little bit finer print typically when it's presented in a text situation. Of course, here I'm drawing by hand, but still, same idea. So it's not a letter X. If I want to have a letter X, I'll tell you, or I'll make that much more explicit. There'll be no X's for letters today, but there is an X, if you will, or a cross for this kind of multiplication. So let's just make that clear on the outset. All right, so how do we go about calculating these answers? Well, let's run through a couple of examples first, and then come back around to talk about why things are working the way they're working. So let's suppose at first that our proton is also moving due north in the same direction as the magnetic field. So these two equations here express how to determine this. This equation here specifically tells you how to find the magnitude. So the magnetic force when the charge is moving to the north will be QVB. But now what about sine theta? And I'm going to leave these alone for the moment because that makes a difference. If the direction of the velocity of the charge is north, that's what we just said, the proton is moving to the north, and the magnetic field is also moving to the north, then they're both moving in the same direction. And we can express those, if we want to sketch those on paper, like this. So the velocity of the charge is moving to the north, and the direction of the magnetic field is also moving to the north, okay, like that. And if that's the case, they're both moving in the same direction, where they're parallel to each other. Now, they're not the same quantity, right? But that's not the question that matters most. The question that matters most is what is their direction. And in this case, because they're both moving in the same direction, that will be the sine of 0 degrees. Sine of 0 degrees, everybody, is 0. So in this case, there is no magnetic force acting on our proton. That's kind of an interesting concept, right? You have a proton, so it's got a mass, it's an object, it's got a positive electric charge, it's got a velocity, there's a magnetic field present. All the things that seem to be necessary to have a magnetic force acting upon an object are there, except that their direction isn't right. The direction is such that you don't get any magnetic force at all. Okay. Now, in comparison, let's do this one here. Part B says, let's have our electron moving in such a way that it's going towards the east. Okay? So if I were to, and by the way, I should make this clear, let's have north going up and east to the right like you would in a normal map. Okay? This means that if velocity is like this, and our magnetic field is like that. Okay? Then the angle between velocity and magnetic field is 90 degrees. Now, sine of 90 degrees is exactly equal to 1, right? In fact, that's where sine of an angle maxes out, isn't it? That's the largest that sine can get. And so, if I do that, then QVB, sine of 90 degrees, which is 1, I get the maximum amount of force. In this particular case, I've already done this calculation in a previous video. I'll just cite the result here. The magnitude of the force is 1.14 times 10 to the minus 20th newtons. Now, by the way, that doesn't sound like that's a very large amount of force, but bear in mind it's acting on a proton, and the acceleration that such a proton would experience would be in the orders of close to 100 million meters per second squared. So it's pretty large for a proton. But that's not really the thing that we're most interested in here. What we're really interested in here is the direction piece. Okay? So how do we determine the direction piece? And this goes back to our friend here, the cross product. So all cross products, whether it's in this particular situation we're talking about magnetic forces, or any other cross product that you care to calculate, they'll all act the same way. This vector here is the first vector, this is the second vector, and this is the resultant vector. So it goes in that order. So if I had vectors, say like, let's say C is equal to A cross B or something like that as vectors, then it still goes in the same order presentation. And that's something, by the way, that's a little bit different here. Order matters, and we'll show that a little bit later. So, in any case, what is this first vector? The first vector is the velocity. So that'd be this one here. The second vector is magnetic field, going up like that. And though a good way to determine, a very simple way to determine how this works is using something called the right-hand rule. Turns out these coordinates have a right-handed system going on, strangely enough. Nature is right-handed, at least in this particular sense. And what does that mean? Okay, so take your right hand. There's mine. Put that in front here. Seen that a lot. What we do is we'll take the first vector and put that in the direction of my thumb. So I'm going to take my thumb and point it in the direction of the velocity. So that's the first vector, right? Velocity. So put my thumb in the direction of velocity, like that, okay? The second vector, the magnetic field in this case going up, I'm going to use my fingers to display that. So thumb for velocity and fingers for the magnetic field. So I have a situation where my right hand looks like this. Now, the resultant vector has to be at a right angle to the plane created by these two vectors. What will that be? That'll be in the direction of my palm. Right now, my palm is pointing up towards the camera. And so the direction will be up. And so our answer looks like that. Interesting how that works. So right-hand rule, and it always works in this fashion. The first vector is the thumb. Second vector is the fingers. The result is always the palm. What direction is the palm pointing in? All right, that's what we meant. So let's try this with a different couple of set of circumstances here. What about this one, 30 degrees north of east? So without worrying about the magnitude so much, let's take a look at what that means for the vectors. So 30 degrees north of east means this. So if north is pointing up and east is to the right in this kind of picture, then 30 degrees north of east will be something like this. There's a 30-degree angle, and there's our velocity like that. Okay, magnetic field still pointing up in this direction here. What does that mean? So let me try this with my hand. So instead of having my thumb pointing perfectly to the right, let's have my thumb angled a little bit. Notice how it's angled like that? It's on purpose. My fingers are still pointing straight up. Now notice something interesting. My palm is still pointing up towards the camera, isn't it? It's kind of wild. So my palm pointing up towards the camera, the direction is still up. So this angle, not being 90 degrees or 0 degrees for that matter, doesn't change the direction. And what that says is it's the plane of the two angles of the two vectors that matters. Whether it's 90 degrees, 30 degrees, 45, any angle in between, which is not 0 or 180, we'll find out, that works perfectly well. This here and this here gives us a plane, and the angle of the resultant vector is always perpendicular to the plane. Okay. Now, if I want to show this off a little bit differently, let me grab out some crayons, borrow these in order to make this point. So let's suppose my velocity vector is the red crayon like this, and let's suppose my magnetic field vector is the black crayon like that. And so in, say, the first example, they're both going in the same direction like that. Again, you can see there's no angle between them, no matter how I got it described. If they're both in the same direction, no matter how I arrange it, if they're both in the same direction, the angle between those two is 0, and there's nothing there. Okay. If, for example, I have the velocity like this and the magnetic field like this, there's an angle of 90 degrees between them. The resultant vector, I'm going to use this little blue-green crayon to illustrate that. See if I can make this happen. There we go. Perfect. That is pointing up towards you folks. So, thumb, fingers, palm. That may be a little bit easier to see visually what's happening instead of having my big hand in the middle of the camera here. Now, if I take this and make this a 30-degree angle, again, notice the plane that these two vectors make is still flat, right? Still here, and this vector still has to be pointing straight up. Now, that tells us direction, right-hand rule, okay? Now, if we want to do the amount, that turns out to be a little bit different then, right? So in this particular example, the magnetic field strength is QVB sine of 30 degrees, right? So that's what we have, 30 degrees north of east. And so if I do that, sine of 30 degrees, oops, this should be a V, is 1/2. And the answer would be, of course, then half of the previous answer. Notice the direction is still up. Doesn't change the direction in this case. Now, let's do a couple others. What if we try to get different directions involved? What if, for example, we have our proton moving down or up or some other direction besides east and north or whatever like that? Okay, first I'll do it as best I can with my hand, and then I'll try it with the crayons. So, in the case of down, take my thumb. That has to point down, so I'll put my thumb like that towards the paper. My fingers still have to point upwards on the page, or to the north on the page, which is going like this. So, kind of strange there. Notice my palm is now pointing to the right, like that. Or, let's see if we do it this way. So, the direction of the magnetic field is still always to the north. The direction of my crayon, if you will, which represents velocity, let's assume that's pointing downwards. Notice how that works. They're both at right angles. Now the plane that these two make is like this. Okay, notice like that. And the direction of the magnetic field will be like that. Now again, this really should be held this way. Make sure I'm pointing my crayon downwards like that. And that is the direction of the magnetic field there. So, if I'm doing magnetic field for this question, if the original velocity is down, then the direction is to the right. So, V is down, let's write that out, and B is north, then the magnetic force direction is to the right, or in this picture, to the east. Okay. Notice how that worked. One more example here. What if our proton is going upwards? So again, take up my thumb. So here's my thumb pointing up. My fingers of my right hand going to the direction here, along north like that. And notice my palm is pointing this direction. It's pointing to our left. Or if I do this again with the crayons, so in this case, here's the velocity now coming up. Magnetic field is going to the north. So thumb, fingers, palm. The direction of the magnetic force will be to the left, which in this map idea we call west. Okay, so let's write that down quickly. All right, so V is up, B is north. Therefore, magnetic force direction is to the left, or west, in our figure here. Okay, so this gives us a little bit of an insight into what's called the right-hand rule. Okay, now a couple of more things to say about this before we leave off today. First off, all of this was done for a positive charge, right? The proton. What if we had a negative charge? Well, probably the best way to go about this is to simply do everything we've done before, the entire process all the way through to the end. But then if you had a negative charge, well, negative must be the opposite. And so if I had, say, an electron involved instead of a proton, then every single direction would be opposite of what is here. So, for example, if the velocity of an electron was down, the magnetic field is pointing north, my right-hand rule shows my palm pointing up, but an electron has a negative charge, pointing to the east, sorry. If the positive direction is east, the negative direction must be west. Right? So everything is just simply opposite if you change out the sign on the charge, which makes sense because of that. All right, last thing to say. This gets a little bit kind of crazy or ridiculous to bring in hands all the time, or to have crayons or markers and trying to balance all these things to make sure everything's acting the way it's supposed to act, right? Stuff like that. And we don't typically draw on a three-dimensional tablet, do we? Or whiteboard or anything like that. So physics people and math people too have a shorthand to represent in and out of a board or in and out of a paper. So if you see a dot like this in the middle of a circle, that means out of the paper, or also out of the board, and so on and so forth. If you see an X or an X inside a circle like that, that's in to the paper. Now, a way to think of that is, say, something like an arrow or a dart, right? If a arrow or a dart especially is pointing towards you, you see the pointy end. If you have a typical dart or arrow with little 4 feathers on it that coming across, then you see the little X that they make if it's going away from you. And so that's a way to represent this. And so instead of saying, say, up, I could have said this symbol here coming towards us, be like that, right? I could have used that symbol instead. Or over here, if I said, the velocity is down, I could have said this symbol like that. By the way, just to say it, a lot of physics people will not bother drawing a circle around the X here when they're doing this in their pictures. I'm putting a circle around it just to make sure we distinguish this, because we already have several X's flying around already. I don't want to get this mixed up with the X symbol that we use for quantities or the cross product symbol, so I put a circle around it to make sure we all understand that is going into the paper, right? But regardless, that is a way to express that. So velocity is down or into the paper like this. Velocity is up or coming out of the paper would be this symbol like that, and so on and so forth. And that's a way to keep these symbols straight and to keep your direction straight. Long story short, if you're trying to figure out directions with magnetic forces, or for that matter, things like torque and some other quantities in physics also invoke this kind of idea of cross products, The right hand is your friend, okay? Because it will tell you thumb in the direction of the first vector, fingers in the direction of the second vector, palm in the direction of the third vector. And it acts like that. Okay. Technical support for these videos is from Cindy Gauchaw and Sophia Turner. Our funding comes from University of Mississippi and University of Southern Mississippi. We filmed these in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Sorolla, thanking everybody for your attention, and clear skies.